Hello and welcome to this course on discrete mathematics, and this is going to be a final lecture, and today we are going to talk about the finite state machine. Well, this finite state machine is quite interesting part, as the finite state machine is at times called as the finite state automation or automata. So as we can simply put, this finite state machines are quite a useful tool to provide certain logics. Not only logics, we can define certain states. We can define different states for an operation, because last time we talked about a manufacturing area where we had different tasks performed, and different tasks can also be stated as different states. There are a lot of other areas where people talk about this finite state machine, and basically it's branched from the so-called auto automata theory. So basically what we have is initially we have this turning machine, then you have this push down automation, then you have this finite state machine, and in fact we have this combinational logic. So we all started with this combinational logics, and from there on we went on to this different parts. If you could recall, we started with the combinational logics, and now we are almost here in this finite state machine. Then comes the push down automation, and eventually it is taking us to the turning machine. Anyway, we are not going to that part now. Right now we are going to just discuss about the finite state machine. Let's see what a finite state machine is, and let's see how they are useful, and let's simply model a simple finite state machine. Let's consider one here. A machine. When we talk about machines in early 18th century or even late 19th century, we always talk about machineries. But as we know, this course, when we talk about machines, we talk about a machine that can perform certain computation and logics, and generally speaking, even we at times call a computer as a machine which has memories as well. Talking about a simple state machines, we do have certain simple way to represent the finite state machine. For example, just giving you an idea, you might have a state 1, so called state 1, and then you might have a state 2, then there might be another state called state 4, say for example, and why not, you might have another state S3. So these are different states, and you might even consider having how the flow happens between these states. And in fact, when you talk about certain flow of these informations, let be clear, no, I don't want to confuse with. So when we talk about these flows, we also have at times we do have a loop in certain state on a certain parameters. Say for example, you have a transition parameter, we call transition parameter. Let's say you have say x here, you have y and x, say y. So we have this transition parameter, and in fact the input is given to this whole system, and it has a chance to transit from one state to another state. And I don't want things to be confused with something called state transition matrix. We also come up with certain matrix by means of the state missions. We don't want to go into that right now, so let's just stop here with this finite state mission, and let's try to examine further on how the state mission would work. Coming to this example of finite state mission, let's see a simple model of a newspaper vending box or a newspaper vending machine, a model of a regular expression. Let's look at these things. In computer logics, in other words the mathematical logics, the computer science engineers are using different operations, operations on set of strings, operation on set of symbols, operation on set of characters. Yes, there are a lot of free monoid constructions are used for such operations. Let's simply see this topic on finite state mission. Let's define the mission itself now. A mission is a system. And what is a system? A system, this mission is a system that has or that can accept input. So you can give an input to the system. It's not just giving input, it has a capacity to store information. In other words, it has memory. It has memory about the previous input. In other words, if you look closely this diagram, say for example there is a movement between S1 to S3, and again there is a movement from S3 to S1. In other words, if suppose you could hold the previous input information or previous information, you can actually perform certain tasks quite easily. That's the advantage of having the memory elements there. So here the mission can remember the previous inputs. In other words, they can store information, and finally they can produce an output. As the mission states the complete internal condition of the mission and all of the memory. That is what we call as the state. So at any instant the current state and the next input determines the next state to be occupied. In other words, we can say that the current state, if suppose the current state is say S2, from there you can go to S4, that's going to be a next state. Or in other words, it all depends upon the input that you are getting as well as the factors like x and y. In other words, any instance the current state and the next input, whatever the input that you get into the current state determines the next state that is going to be occupied, as I told you. So it depends upon your x that is being given to S2, and based on that you are going to S4. And again while you are in S4, it again determines another factor on how we are going to transit to the next state to be occupied. Finite state mission. A mission with a finite number of state is a finite state mission. Now we have defined what is the mission, what is the mission state, and now we are defining what is the finite state mission. A mission with a finite number of state is a finite state mission. Formally we can have, like for example, S is a finite set of states, S not S1, S2 till Sn, and I is the finite set of inputs. So you have I1, I2, I3 till Ik. A state transition function, S implies S, where X is an element of I. If the mission is in state Si, S sub I, and the input X is received, the next state is F of x, or f sub x is I. So the finite state of transition function f equals f sub x of such that x is an element of I, or in other words x is the input. So the triple SIF, which is the finite state, finite input, and the finite set of transition functions, defines the state, finite state machine. In simple language, we can simply say that the same things: the finite set of state, finite set of input, and finite set of transition from one state or one finite state to another state is specified for a specified input is to be defined. One of the state is designed as initial or starting point. We always have a starting state from where we started. Another state is designed as a final state or accepted state. Let's see here more. So finite state diagrams are labeled diagraph. The one I gave as an example is not really a pure example. We are going to see some simple symbols exactly how we define this finite state machine. States are represented by circles. In fact, we have did the same thing. The state names appears with the circle, and the final state is indicated by two concentric circles. Again, the transition are represented by arcs. You just put an arc that connects one with the other state. Next, the arcs are labeled with input that initiates the transition. We are going to consider this example of finite state machine for which we use the newspaper vending box. And the basic idea is that the paper price is 30 cents and we are going to accept the nickels, dimes and quarters. And we just assume that there is no change given, there is no option for giving the changes. So we want to create a state, finite state machine model for this vending box. Let's say here you have this different state functions given by f. We can see this simple table where we can basically define the names as the values of coins that need to be deposited to purchase the paper. And what you have here is the input. You can give either say 30, 25, 20, 15, 10, 5 and 0. So initial state what you have is 30, the final state is 0, and your input can be nickel, dime and quarters. And the transition function, that is f of f sub n 30 equals 25, f sub d is 25 equals 15, f sub q is 25 equals 0, and etc. So these are some of the functions that we can think about. On to your right you can see this table that defines how this how this transition happens from the one state to another state, and where n, d and q represent the nickel, dime and quarter. So for example, if you are looking at say we have different options of nickel as well as the different options for dime, and quarter is given to us. You can, considering the fact of given state yes, which can be 30, 25, 20, 15, 10, 5 and 0. Accordingly you can have the input. So you can expect the inputs from these conditions. So the diagraph notations are given here. A circle that represents the state, and you can see as if an arrow heading in for the initial state with the initial state with the circle. That represents the initial state. Then comes the final or accepted state, that is kind of two concentric circles that represents the final state, and jumping from one state to another state, or in other words the transition from one to another is called it has been represented by means of this arc that you have here, and here as an example as input is q. This is the basic notations, and here is how the Venn box diagraph is given to us. So now you can relate how things are going to happen. If you relate this with that of the ones we have seen earlier in this part, for example here, if you are talking about the dime, we have 20, 15, 10, 5 and 0, and if you talk about the states, you have 30, 25, 20, 15, 10, 5, 0, and for these states you could have equivalent dime, quarter as well as the nickel. Say for example, as you can see, the starting point is 30 and it goes on with the nickel of 25, 20, 15, 10, 5 and 0. And if you want to talk about the quarter, it goes to 5 and 0 every time. And if you are talking about the dime, it goes from 30 to 20, 25 to 15, and 20 to 10, 15 to 0. In fact, yeah, that's how, in fact it's not from 15, 10 to 0, it also goes from time, and also 5 to 0. So the different transitions have been given, and you can also see here the arrowhead clearly shows us the direction in which the entire flow happens. So based on that you can in fact give the whole stuff. And if you are familiar with the graph that we have seen during the graph theory class, do you think we can relate something over here? In fact, in graph we talk about the nodes and vertices, and we talk about edges that connects these vertices. How about here? Do you think that when you have a real world problem that has been mapped with a state transition like finite state missions, and does a representation using graph can help you to solve certain problems? That's one of the things that I want you to examine. Why don't you try out and see what are the properties of graph might be useful if you are really working out on a finite transition system, finite state mission. And of course this finite state mission works on a completely different principles, and our objective is completely different. But for the way of evaluation, for way of justification, the way of modeling things, graph can really helpful for us. And in fact once you have things in a form of state diagram, we call such as state transition. In fact you can come up with, as in case with graph we came up with the adjacency matrix, likewise here you can come up with the state transition matrix. Yes, the state transition matrix is another way in which we can also represent, and the whole process of such things can lead us to something called stochastic process. Yes, the probability based transition, and I don't want to go deep down on that aspect today, but there is this option that you have. You can have a look at this, even if you just try to search what is the state transition matrix. This will help you to understand more about this, the whole system. And in fact with such matrices we can perform various tasks, and many real world problems can also be solved using such scenarios. So here we have given another scenario with the vending box there. So regular expressions that are being used here is like the base is the empty set, and here is the element is a null string, and each individual symbols in sigma. For recursion, concatenation we say RS, union is OR such that X, then comes the clean closure, and in fact the clean closure is something that you can see in the mathematical logics, the computer science. We say clean star or clean operation or clean operator, in other words, or clean closure is an urinary operation either on set of strings or on set of symbols or characters. Basically this clean closure is the urinary operator that performs operations on sets, strings, or set of symbols or set of characters. These regular expressions in fact has been introduced by Stephen Klein, and of course it's again useful for the automata theory. So in basically sometimes it means 0 or more. Then comes the nothing is a regular expression over sigma x except for objects defined here 1 and 2. Okay, let's go further and see how such things can be done for with the FSM, that is a finite state machine and regular expressions. We can design finite state machine that can be used for determine if a string belongs to a regular set of corresponds to a specific regular expression. So when you have a regular expression given to you and you are trying to determine if a string belongs to this regular set of corresponds to the specific regular expressions, we can perform using the finite state machine. So you got this idea. So we can design a finite state machine that can be used to determine if a string that belongs to the regular set that corresponds to a specific regular expressions. Coming back to this idea of this regular expression, you have a given alphabet, say A has a set with A, B, C, and in this example we have B, A star B. So for example we could say A times B if you wish, but since we talk about strings expression, we can refer it as A star B. And in the input you have this input cycle as A star, and in this loop, as long as there is A, it stays in this initial state or starting state, and with B it goes to the final state, which is represented by means of the the concentric circle. So there we get the combination of A and B, or that is A star and B. That is going to be your output in this regard, in this case. So example with the AB such that BA, C star. So you have this input onto your left or the initial state, and then with A you are going to the upper part, with the B you are going to the lower part. Again with B you are coming to the lower part, and with A you are going to upper part, and you are reaching your final state, which is represented by means of this symbols here. So here is your initial part, of final. So this is a simple example of how to represent using such strings. We know that with A it's going up every time, whether it's here or here, and with B it's coming down whether it's here or here, and this is an intermediate state. We have this part here where we have this intermediate state, and there might be several intermediate states depending upon what our output is, what output is needed. You can have several different intermediate state, and there may be several different directions in which it might go. It all depends upon our output that is needed, and basically you have to formulate it such a way. So does the following mission corresponds to A such that B star C star? So this is another kind of complicated. Here we have A is with the A we are going to the upper one, and with the B you are going to the down part, and again there is some transition happens within this part. If you look at, with A it stays there, and with B it stays there in the loop, and whenever there is in the B, whenever there is A it goes to this A part, whenever it's B it goes to the B part that's below, and if there is C then it goes to the initial or final state. So this is a simple logics and simple way to express the finite state machine, and by now you know some idea about how the final state machine can be performed and expressed. So there are a lot of other areas where you can go for using the finite state machine concept. We simply saw how it can be done using winding box or regular expressions. There are a lot of other places where you can use this finite state machines, and it's one of the efficient tool for us to represent the real world problem using a state transition, the so-called state transition machines. Yes, we have seen several parts in our course all throughout. We talked about logics, we talked about propositions, predicates, we talked about the quantifiers, the universal quantifiers, the existential quantifier. We talked about numerical parts such as the number theory. Apart from number theory, along the side we saw different series of numbers, like for example sequences. We talk about sequences, recursions, mathematical inductions. We talk about sets, functions, relations. We talked about algorithms. We talked about graph theory, and finally today we talked about the finite state machine. There are a lot of interesting features that we learned throughout this course, and I really hope that these parts are very useful for you to go on with other courses that you are going to study in your computer science engineering program. And these are all foundation courses, and I wish you can do more by yourself, even like try to do a lot of homeworks and try to solve these problems that are given to you. Practice more. You can collaborate with your friends, but try to see whether you would be able to finish by yourself. Yes, that's the idea. Try to get the concept. Apart from this lecture, you can also refer other books. Apart from the textbook that I mentioned in this lecture, you can also refer other books or other materials that you find interesting. But the main idea is to grasp the whole concept and try to understand the principle behind it. I hope this whole class is very useful for you guys to explore a lot about the discrete mathematics, and this logics can be very useful for programming as you move ahead with this course. I am very happy to be part of this course and glad that I shared some of the thoughts that I had in this course with you guys. I am wishing you good luck and goodbye.